Okay, so the power then always goes to a main contactor. The main contactor is an electrically operated switch that can break the power, okay? And the main contactor is part of the emergency circuit. So the e-stop is what energizes and de-energizes the main contactor, okay? So they call this a contactor and not a relay. And there's a difference. In a contactor, there's a wire hooks here, and there's a jumper that moves in and out that's conductive that goes between them, so it breaks the load twice. And the reason for that double break is that it reduces arcing because it opens faster. You get a bigger gap quicker. And so that's a contactor. So this is a contactor. This is the e-stop contactor. And then we have other contactors. These guys down here are also contactors and do the exact same job. They're just sized for the motor. This one's sized to handle the load of the entire panel, and these are sized to handle the load of an individual motor. Okay?
Sorry, quick clarification. So a contactor is similar to a relay, it just has less arcing.
Yes.
Okay. Like
yeah,
there's like a difference.
It's always contactors are always double break, where relays are only single. They only break.
So it's a contactor, a relay, but a relay is not necessarily a contactor.
Correct.
Okay, great.
Yes, that's exactly right. Okay, so they function the same way. All right. So, so that's how we interlock the safety circuits through the main contactor. Okay, and so like I said, every panel we build, we will have a main contactor, a main switch. Okay, so then from the main contactor, we actually go up to circuit breakers to supply power to various things. Now, these are all 3-pole circuit breakers because these are supplying 240 volt 3-phase power to motor equipment. And then we also have a transformer, okay? Now, what a transformer does is change the voltage. And when back in the good old days, Edison and Westinghouse were battling it out for electrification in the U.S. Edison was a proponent of DC, and Westinghouse was the AC proponent, along with Tesla. And Tesla and Westinghouse won out. And the reason is there's no easy way to change voltages in DC, all right? Or at least there wasn't for a very long time. And so Edison had to transmit power at a low voltage, which took big wires and couldn't travel very far. Whereas Westinghouse could use a transformer to take the voltage from, in the case of the first installation, Niagara Falls, jack the voltage up really high through a transformer because they work in both directions, and then drop it back down again where you want to use it to a safer voltage. So transformers are change the voltage by magnetic coupling between two sets of coils, and the ratio of the coils determines how much. So this transformer is taking 240 volt AC through a 2-pole breaker, okay, and changing it into 120 volt AC, right? So the 120 volt AC is our AC control voltage, and we're using a transformer to do this. We could bring the 240 directly to other things that have a wide-ranging input, but the reason for using a transformer is to get some protection against lightning and surges and such, because the magnetic coupling in here won't pass an enormous surge of current. It'll just get soaked up in the transformer. So we try to build things with multiple levels of protection. And then I don't use PLCs with 120 volt input power. And the reason I don't is because I can hide the PLC behind another power supply that changes the AC to 24 volt DC and then run the PLC off of that. And that's just an added level of protection. If I get struck by lightning, I want as many things to get cooked before they get to the PLC, which is the brain of the whole thing. So that's the reason for splitting things up this way.